Okay, everyone, I'm Hongwei. I came from China, Tianjin University of Technology. Today, I'm very happy to share my research work with you. The title for my presentation is Design Synthesis Crystal Growth of New Nonlinear Optical Crystals. My presentation will be divided into three parts. The first part is background. We know the laser is one of the greatest inventions in the human beings' technological history, and its application have covered all aspects of our daily lives. But the different application needs the different wavelengths of laser. For the solid state laser, they can only produce the laser in the near region. So the SIG of nonlinear optical crystals is best way for the solid state laser to achieve the wavelength expansion. During the past decades, many nonlinear optical materials have been discovered, but these materials can only work very well in the near UV and visible region. But in the UV, especially in deep UV and IR, these materials cannot output the high energy lasers. To discover the new nonlinear optical materials in this wavelength range is still the current research hotspot. My research work is also focused on on these wavelength ranges. Our strategy contains two aspects. The first one is a structural optimization. It means we will choose the classical nonlinear optical crystals as a structure template, and then through the element substitution or rearrangement of its building units to improve the material structure. The second one is anion mixing. We know, according to the trans anion group, the nonlinear optical property of the materials mainly from the anion groups. So to combine the different anion or anion groups to construct the mixed ionic compounds can better integrate the property advantage of the different classes materials. So by doing this, we have done four parts of the work. The first part work is the deep UV KBF-like compound. We know KBF is a source material that can output the deep UV laser by the direct SSG. And the excellent nonlinear optical properties of KBF is mainly from its BE2 BO3 layer. In this layer, it contains the high conjugated BO3 triangles, and this BO3 triangle have the co-play arrangement. This arrangement makes KBF have the large SIG response and suitable by reference. And in this layer, all the terminal BO bonds are connected by the barium ties. It removes the dangling bonds, so the cut-off edge of KBF can reach to the deep UV 147 nanometer. But between these layers are very weak KF ionic bonds. It makes KBF have very strong layer habit. The maximum thickness for KBF is only 3.7 millimeter. It make KBF cannot output the high energy laser. And to grow the KBF need to use the high toxicity barium oxide as the raw materials. So it may grow KBF very difficult. So we can say the excellent nonlinear optical property of KBF mainly from the B2, BO3 layer, and but the weak layer connection make it has very strong layer habit. So in our research, we want to use the there's some problem with this. we realize the zinc, lithium, aluminum ties have the similar coordination with the barium ties. So we want to use these ties to substitute the barium to avoid the usage of high toxicity barium oxide. And in order to enhance the layer connection, we choose the suitable size ties to induce the covalent bands covalent bands to develop layer KVF into three-dimensional framework. There is some problem with this photos. We synthesize the cesium, zinc, borate, and rubidium, barium, aluminum, lithium, aluminum, borate, fluoride, and for both these two compounds, we can grow the centimeter size crystal, especially for the rubidium, barium, aluminum, borate fluoride. Based on the SIG of this crystal, we have achieved the 266 nanometer laser output, and compare with the commercialized cell view, we can see this compound have the smaller work-up angle and a large acceptance angle, and it's non-hygroscopic. So it is promising for the high energy laser output at 266 nanometer laser output. And our second research work is mixed coordinated boron phosphate. Here we mix borate group and phosphate group together to design the deep UV nonlinear optical materials. We know beyond KVF compound, the silicon and phosphate with the SiO4 and PO4 tetrahedral as a basic building unit can also produce the deep UV cut-off edge. But for the tetrahedral compounds, because the tetrahedral basic building unit is very difficult to polarize, and the tetrahedral building has very weak structure and anisotropic. So they generally have that tetrahedral compounds generally have very small SIG response and by reference. But for the deep UV nonlinear optical materials, it needs large SIG response and a large by reference to achieve the phase matching. The recent research from Chen's group and Pan's group and Ross group have put forward some strategies to enhance the SIG response, and they have synthesized a series of SIG enhanced compound. And for this compound, we can see the SIG all larger than the 1 times KDP, so it can satisfy the SIG requirement, and their cut-off edge are shorter than 200 nanometer, so it can reach to the deep UV. But for the by reference, we can see for all of these materials, it's smaller than the 0.3. But for the deep UV, their by reference should be larger than 0.05. So for all these materials, the by reference is too small for supporting its phase matching in the deep UV. In order to improve the by reference of phosphate, our strategy is to introduce the pi-conjugated BO3 triangles into the phosphate to construct a new types of mixed coordinated boron phosphate. But we know for the phosphate, for the boron phosphate, because the connection between the BO4 and the BO4 will make the bridged oxygen have the ideal -2 band valence. So for the most reported boron phosphate are the tetrahedral boron phosphate. But the connection between the BO4 and the BO3 will make the bridge oxygen overbundled. So the mixed coordinated borophosphate is still rarely researched. In our research, we have realized that to increase BP ratio in the borophosphate may be favorable for the mixed coordinated borophosphate, because in bone-rich borophosphate, the connection BU4 and BU4 can avoid the direct connection between the BU3 and the BU4, so it can stabilize the mixed coordinated borophosphate. By doing this, we have synthesized a series of mixed coordinated borophosphate. In the ammonium borophosphate, we can see it has large SIG response, by reference. The by reference for this compound is 0.092, which is even larger than that of KBF. And as we know, this is the largest by reference among all reported borophosphate. And in this compound, the most one is cesium borophosphate. It crystallizes in the non-central symmetric space group R3, and it inherits all the excellent structure genes of commercialized LBO, BBO, and KBF. We can see this is structure for the CBPO. The basic building unit for this compound is B307. It's similar with that of LBO, and this B307 group have the co-play arrangement, which is similar with beta BBO. This arrangement can make compounds have the large SIG response and large by reference, and all the terminal BO bands also connect by the BO4 and the PO4. So it's remove all the dangling bands in the structure, which is similar with that in KBF. So CBP, the cut-off edge of CBP can also reach to the DPUV region. And between this layer, we can see it's not the way KF bands, it's the very strong BOP covalent bands. It's a three-dimensional framework. So CBPO can totally overcome the layer problem of KBF. Actually, we have measured its thermal properties. The measurement shows CBPO melt congruently, and it have no phase matching from the room temperature to the 600 degree. 630 degree is close to its melting temperature. So this compound is melt congruent and have no phase matching from the room temperature to the 600. So through the TSIG method, we can grow the city size crystals for this compound. We can see the thickness for this compound is around 8 millimeters. So it totally overcome the problem of KBF. And we also measured its SIG response. The SIG response for this compound is around 3 times KDP, but for KBF, it's just around 1 times KDP. So the SIG response for this compound is also larger than KBF, and the cut-off edge for this compound is 165 nanometer, and at 190, it still has very high transmittance. The transmittance is higher than 80%. And we also measured its reflective index by the minimum deviation angle method. We can see that by reference for CBPO is around 0.75 at 532 nanometers, which is comparable with that of KBF around 0.08. And with this reflective index, we can calculate its phase matching. The phase matching calculation shows that the phase matching limit for CBPO is 199 and 188 for SIG and THG respectively. So it means CBPO can achieve the UV and deep UV laser output by directly SIG or THG. In addition, we also measured its SIG coefficient by the Mark-Rangin method. For CPO, it belongs to the 3 points, so it has 2 large SIG coefficients. For D11, it's around 5 times KDP, and for D22, it's around 3 times KDP. And with this problem, we can evaluate its potential application at UV and deep UV. Firstly, we evaluate its application at UV 200 nanometer laser output application. We know for this wavelength laser, it's important for the semiconductor processing. We can say CPPO can output this wavelength laser by SIG, and compare with the commercialized beta BPO and the CLBO, we can say CBPO with the largest effective SIG coefficient at 266 nanometer laser output, and it has the smaller work-off angle, and it have weak hygroscopy. So for this compound, it's very good for the high power laser output at 266 nanometer laser output. And in addition, this compound also can achieve the 193 laser output. 193 laser is a light source for the laser machine, and this compound with other compounds that can achieve 193 nanometer laser output. We can say, firstly, KBF can also achieve this wavelength laser output, but KBF have very strong layer habits. The maximum thickness is only 3.7 millimeters, so it's very difficult to achieve the high energy laser output with this very thin crystal. And for LBO and CLBO, they also can achieve this wavelength laser output by the SFG. But the bireference is too small. It's just 0.004 to 5. So this very small bireference makes them cannot be pumped by the metro lasers. For BBO, because the cutoff edge for BBO is around 190. So at 193, it will have very strong absorption. So for beta BBO, it's also difficult to achieve the high energy laser output at this wavelength. But for CPPO, we can see its thickness crystal are available, and because it has the suitable bireference, so it can be pumped by the metro lasers and the transmittance at 193. CPPO also has very high transmittance. The transmittance is higher than the 80%. So the CPPO is also important for the deep UV 193 laser output. And but when in our previous growing crystal, we can say it contains some inclusion. It's because the CPO is for rich compounds. It has very high viscosity. So in previous growing crystal, it contains some inclusion. It makes crystal unclear. But after we optimize the crystal growth condition, we can grow the better crystal recently, and we can say the crystal we grow recently is very clear and no FBS including. So we believe that high quality CVPO can be grown, but more attempts for the crystal growth condition may be needed. This is our research work in the DPUV part. And we also do some research in the for the ion nonlinear optical materials, but because the time limit, I just go through these two parts very quickly. The best part research for the I origin is the beta BGSE. We synthesize this compound by structural rearrangement of alpha BGSE. We know the alpha BGSE have been considered as the best ion nonlinear optical materials that can be pumped by the 1 micro laser. But for this compound, it have very low symmetry. It's crystallized in the PC space group. In the PC space group belong to the monoclinic system. In the monoclinic system, the crystallography axis ABC is not same with the dielectric axis XYZ. So it's make its application inconvenient. In our research, through the structural rearrangement, we change its basic building units from the C2 spectral tetrahedra into the T2 spectral tetrahedra. We know that T2 spectral tetrahedra has the highest symmetry than this one. So beta with this as the basic building unit, beta BGSE crystallized in the higher symmetry was a rhombic space group PM21. For the rhombic space group, the ABC is same with XYZ. It's good for its application. And the more important thing is that we can see in beta BGSE that.
Let me interrupt 1 second. You got it. 2 minutes.
Okay. The T2s tetrahedra have the same orientation. So for beta BGSE, it can generate a larger SIG response than beta BGSE. So beta BGSE might be a promising nonlinear optical materials. And we also noticed that for the ion nonlinear optical materials, there are two main classes materials. One is chalcogenides, the other is oxide. And for the chalcogenides, they can generate a larger SIG and wide IR transmission, but band gap is more. The situation is upside for the oxide, so we want to mix them together to balance its properties. So we do some research for the oxygen ancogonide through the rational substitution oxygen and fluorine. We synthesize some malachite-like structures. They can better balance the band gap and IR transmission, and we also combine the oxygen sulfur and fluorine, and we synthesize the fast and single symmetric and unsynchronized fluoride with a good balance among the SIG band gap and IR transmission. And recently we use the mixed anionic groups to break the symmetry of the tetrahedral building. We synthesize a new oxychalcogenides with the triple and polar duality. And we discover from the single anion compound to the mixed anion compound, the bireference can be greatly increased. And we also write a review paper about oxide ancogonide and its application in the nonlinear optical materials. In summary, through the structural optimization and NI mixing, a series of new UV and ion nonlinear optical materials has been synthesized. In them, this compound has the KBF like structure, and it can generate 296 nanometer laser output by direct SG. And for this compound, it contains all the excellent structure genes of LBO, BBO, and KBF. It's promising as the deep UV nonlinear optical materials. And for beta BGSE, it can exhibit higher symmetry and larger SIG response than alpha BGSE. So it's potential as the ion nonlinear optical materials. And also we mix oxide and chalcogenides to synthesize oxide ancogonide, which can better balance the key properties for the ion nonlinear optical materials. They may be potential as the IR nonlinear optical crystals. For this research work, I want to thank my research group, and I also want to thank my supervisors and collaborators. Okay, this is my presentation. Thank you, everyone.